Dennis is actually out on the coast for a few days, so he's not able to attend this meeting. So normally it would fall to our Vice President, who is Judy Anderson, and she is away in Churchill, I believe. So I don't think she got. Oh, gee, you're back. Okay. Well, if Judy shows up, she can certainly take over, but for now we have to get the meeting rolling. So, yeah, again, I just want to thank everybody for attending, and for those that are here in person for fighting the parking situation out there. So we have a jam-packed agenda this evening. We're going to start with Gail Weiss. She's going to talk about camelopardalis. Now, I would have practiced that if I'd known I was going to have to do the announcements here. So it's camel, I guess. So you want to come up and just take over? Everybody like to welcome Gail.
Once upon a time, because that's how stories should start, the sun did not know its way across the sky. The Creator knew that this was not a good thing, and so he looked around to find a guide. He looked through all the animals of the earth, and he finally settled on the giraffe. "You are good and very tall with your magnificent horns," said the Creator. "I would like you to guide the sun on his daily journey." The giraffe was very pleased to accept this important job, and every day he led the sun from the east to the west of the sky. And every night he would brag to all the other animals about his important job, the most important job in the world. After a little while, the sun was able to do the job on its own, and he said thank you and goodbye to the giraffe. The giraffe was a little bit miffed about losing his job. So for a while he tried to distract the sun. And although the sun went a little to the north and a little to the south, he had remembered the basic pattern. Soon the Creator found out what was going on, and he summoned the giraffe to his presence. "Why are you trying to distract the sun?" asked the Creator. The giraffe shuffled his feet, but he couldn't come up with a good answer, because he was a little ashamed of his behavior. The Creator thought for a while, and then he decided, "Because you did a good job, I am going to let you keep your height, except for one thing. Because of your attitude, I am going to take away your horns. But if you are humble, maybe one day you will get them back. I might send them to you in a way you don't expect." With a swipe, the giraffe had his horns cut from magnificent horns to shortened stumps. Just look at a giraffe today, and you will see that this is how it is. One day you might get your horns back. I might send them to you in a way that you don't expect. With a swipe, the giraffe had his horns cut from magnificent horns to shortened stumps. Just look at a giraffe today, and you will see that this is how it is. And to this day, you'll see giraffes looking curiously around to see if you have his horns. And they will always be humble, even though they are the tallest animal. Camelopardalis is probably the least familiar of the large constellations in the northern sky. Its borders take up a very large area, but not very many books even mention him. It lies in the space between the head of the Great Bear and Cassiopeia, which is up there. And this region was left blank by the Greeks since it has no stars brighter than fourth magnitude. But it does have a fair number of interesting deep sky objects that are visible with our telescopes. I shouldn't be vain, I should wear these. Most of the black gulf between Capella and Polaris belongs to this constellation. Its name, Camelopardalis, suggests that it's a cross between a camel and a leopard, which is a feline, by the way. But this animal is, in fact, a giraffe. The giraffe faces the Great Bear in the sky, which is a rather dangerous position for such a gentle animal. Almost half of the 88 constellations are animals. You'd think with all that they could have worked in a cat. Now, if all of these animals were gathered together, they would make a very fine zoo. And this zoo would contain several creatures that are not seen in any other zoo, such as a unicorn, a phoenix, and a sea monster. Camel leopard was the name that the Greeks gave to this constellation because they thought it had the head of a camel and the spots of a leopard. On page 270 of your Observer's Handbook is a pronunciation guide for the constellations. This is one that I did have to look at. People say it all different ways. However you want to say it is fine with me. The giraffe is a fairly modern constellation. He's very shy, so he hides well because none of the animal's major stars are brighter than magnitude 4. It's too bad he's so difficult to see because really he does sort of, kind of, maybe look like it, might kind of look like a giraffe. And Spruce Woods is the only place that I have even been able to see him. He's just too dim to see from the city, and even at Glenlee, he's in the north, so we're looking in the wrong direction. He is circumpolar at our latitude, which means that he never sets. In the winter, he appears to be standing on his head, so you might want to wait until summertime to look at him, when he's right side up. So to find him, first get your bearings. With your naked eye, find Capella. Now, if you're not sure which star is Capella, start at the Big Dipper, and instead of going north to find Polaris, follow the top stars and go to the west of the sky. And then as you approach the Milky Way, that bright star that you see is Capella. Now, moving northwest from Capella, you enter Perseus. So halfway between Capella and Myrfak, which is that bright star in Perseus, that's the giraffe's feet. Halfway between Myrfak and Polaris, that's his backside, and now you can see where his neck is. So, now that we have his anatomy sorted out, let's take a look at Let's look at Beta. This is the brightest star in Camelopardalis. This is 4th magnitude. It's a yellow supergiant. It's roughly 100 times the size of our sun, and it's about 1,700 light years away. Beta is on the RASC double star list in case you're working on that. And 6 degrees north is Alpha, which is nearly as bright. Its magnitude is 4.3. Don't ask me why Beta is brighter than Alpha. I don't know. Alpha is a blue supergiant. It's 4,000 light years away, and its diameter is about half the size of Beta. Northwest of Alpha is Gamma, which is magnitude 4.6. This star is twice the size of our sun, and it's about 180 light years away from us. And our giraffe has a few nice double stars. One of them is 1 Camelopardalis, which is also on the RASC double star list. This is a pair of 6th and 7th magnitude stars that are separated by 10.3 arc seconds. The brightest double in the giraffe is 32 Camelopardalis. Now, this one is relatively easy to find. It's located along the line from Mizar, which is that multiple star in the Big Dipper's handle, and go to Polaris from there, and it's about 7 degrees from Polaris. This has a combined magnitude of 4.8, so it's fairly easy to find with binoculars or a finder. And the two stars are separated by only a half of magnitude of brightness and 22 seconds of arc. The constellation was invented by the German astronomer Jacob Bartsch in 1614. This is an example of the general mopping up of the sky that accompanied the birth of modern science in the 16th and 17th centuries. This was a time when Europeans were becoming familiar with the strange creatures of Africa. The giraffe is often overlooked by observers because it has no Messier objects. But there are some very nice deep sky objects to be seen. You'll just have to work a little harder to find them. At first, it seems to be empty of stars, but it has a small treasure trove of interesting objects for the motivated observer. Two of our nearest galactic neighbors are in Camelopardalis. IC 342 is almost hidden in the stars of the spiral because it's halfway between a normal spiral and a barred spiral. That's what that means. This was discovered by William Frederick Danihan in 1892. It is of particular interest because it's a member of the local group of galaxies, which includes our own. IC 342 is only 10 degrees above the galactic plane, and so it's obscured by the stars of the Milky Way. So it's difficult to get an accurate measurement of its distance. It's a face-on, it's magnitude 12, and it's very large, 15 by 15 arc minutes, which is half the size of the full moon. This is one of the largest galaxies in the sky, and it's probably among the half dozen that are nearest to us. M31 and M32 are the only spirals that are likely to be closer in the Milky Way system. IC 342 is 25 light years in diameter, and its luminosity is 10 million times the brightness of our sun. NG 2403 is a large, loose structured spiral galaxy, which is located pretty much in the middle of nowhere. This is one of the nearest spiral galaxies beyond the local group. It's an outlying member of the M81 group of galaxies. It's 8 million light years away, so it's 4 times further from us than M31, the great Andromeda galaxy. Its size is approximately 16 arc minutes by 10 arc minutes, and although it's further away than IC 342, the light is concentrated into a smaller area, so it appears brighter. Its magnitude is 8.8, which is really bright, and it's one of the most distant objects that can be seen with binoculars. Its diameter is 37,000 light years, and it has a total luminosity 4 billion times of our sun. Imagine that. This is a rather young galaxy, as galaxies go, and it's still evolving. There are a number of blue giants in the arms. This bright spiral was missed somehow by Charles Messier for some reason, and it's, yes? No. Oh, all right. Okay. This bright spot galaxy was missed by Charles Messier for some reason, and its discovery was left to William Herschel in 1788. Are you sure? You don't sound too sorry for that. Onward. This galaxy was discovered by by William Herschel in 1788. Edwin Hubble detected Cepheid variables in NGC 2403 using the Hale telescope, making it the very first galaxy beyond the local group in which a Cepheid was discovered. Now let's take a little deeper to look and find some less observed objects. NGC 1502 is a tiny but rich open cluster that has about 25 stars. The diameter of the cluster is 8 arc minutes. It's right under the giraffe's tummy, 37,000 light years away. Its brightest star is 5th magnitude, and for you football fans, it has a nice blue and gold double on the northeast side. And there is a string of stars that are mostly 8th magnitude, nicely seen in binoculars, and it seems to splash into the open cluster, 1502. This is on the Explore the Universe list, in case you're working on that. And this asterism is called Kemble's Cascade in honor of the late Father Lucian Kemble. This cascade contains about 20 stars, nearly in a row, and it stretches over 2.5 degrees, or 5 times the diameter of the full moon. NGC 2523 is a barred spiral galaxy with an unusual structure. It has a bright bar that's surrounded by a swirl of knotted spiral arms. This one is magnitude 12.7, so it's a little bit more of a challenge to find, and it measures right for a planetary at magnitude 12, but it measures only 1 arcsecond in diameter. It appears as a light blue disk, and it has markings in the center that are similar to NGC 2392 in Gemini, and that name has been changed to the Lion Nebula, another key one. IGC 3568 is another planetary nebula. It's about 9,000 light years away, and this is known as the Lemon Slice Nebula. See cats drinking lemonade? Get it? Okay. This has a diameter of about 4 light years, or about 800 times the size of our solar system. Imagine that. It measures 18 arcseconds across, and at magnitude 11.6, it is fairly bright for a planetary. It looks like a tiny little disk of light, like a star that you just can't quite focus. I'll bet that not very many of you have ever taken a look in the direction of Camelopardus the giraffe, but I hope that I've inspired you just a little bit to take a peek in his direction. When we say that giraffes have it over all the other animals, that's not just a tall tale.
How was Churchill?
Tell a joke, do a dance, do something.
Well, I'm not very good at dancing. Churchill was good. I did actually get up last night at 2, which was equidistant between sunset and sunrise. And, no, 2 wasn't equidistant, but in any event, there was nowhere near enough darkness to see any kind of star. So here I thought I might see aurora or something if I was up there, but not a bit. But everything was coming into bloom and the birds were out and all of that, which is why I went. So Dennis is on the coast, I understand, and different scopes while you are thinking about equipment, or maybe for some variety over what you typically use. However, there is a bit of an issue. Mike Caracas has these in his garage or his basement, and he would like some help storing those when they're not in use. So if you have space and you're thinking you might be able to make a little bit of it available, and you would be open to being contacted by people who want to borrow a scope, you can come and see me or see Mike Caracas, who's not here either. But I guess we'll handle that. So we've got so far on the move outreach event and storage space for loaner scopes. We're interested in ramping up some of the outreach events that we have. It's not really a great time of year right now to have these events, but the public seems to have it in mind that at the drop of a hat, we're interested in going out and showing them the sky, even if it's dark at 11 p.m. and their 5-year-old has to go to bed. But this is going to continue into the fall. In fact, we've been contacted by the Assiniboine Friends of the Assiniboine Park, or Assiniboine Park Conservatory or something. They are interested in having indoor events at the least. But if you would like to volunteer for some of these outreach events, let a member of council know so that we can put you on the list. And we're also looking for people who would like to help out being hosts for member observing nights out at Glenley. This will involve setting up a scope that's out there, not necessarily the dome scope, but just being there, opening up for people, and showing some folks the sky who may not be so familiar with their own equipment. But it's a nice time to sort of socialize and have coffee in the dark together. There is a RASC store, which you can get to from a link on the website. You can order, I think it's hats, pins, shirts, cups, that kind of thing. And there's an internment ceremony July the 7th at 10:30 in the morning for a former very long-term member who was very generous in his final bequest to the Royal Astronomical Society of Canada. And this is taking place at the Neil Bardall Funeral Center, which I think is out near Red River College, right across the street from them. Okay. So you can contact me or other members of the council if you're interested in doing any of those things. There is still some frustration with use of the groups.io email listservs that we have that replace the former University of Manitoba sponsored RASC list. Now, a lot of people say they don't want to get bombarded by massive numbers of emails, but we would like you to register for this RASC Groups.io function so that you can have general conversations. Post a picture of something you took. Right now people are doing that, but there's really only 30 or 35 of the over 200 members are participating in the general forum, it's called, of the RASC email list. So this is some instruction for that. You go to the RASC Winnipeg RASC in the search box when you go to groups.io, and you join that. If you're not already a member, put in an email and password, and click on the subgroups. Now this can be astrophotography, it can be astrosketching, it can be the general forum, but at the least, the general forum is where people can send those emails to communicate. You know, there's a auroral outburst happening, or look at the noctilucent cloud clouds, they're up in the sky. It's just about time for that. I think it's already started. I had 2 reports that it was up on. So you can join which groups you would like, but I really encourage you to participate in that manner. At least you'll hear the conversations amongst the members. Right now it's kind of one-sided, and if you just get the main stuff, that's the formal announcements from the council or via national. So members observing night will be tomorrow night out at Glenley, and there's a map to that place on the back of Winnicentrics, last issue. If you don't know how to get there still, you can talk to me at the break. It's pretty easy. So the next thing on the menu is What's Up from Brian.
We watched it.
Yeah, you saw it.
We saw the bank coming down the side. They sort of parted, like the Red Sea. And then slid up into Winnipeg and pissed off.
Well, I didn't really because I didn't get outside. I saw from inside. But well, I'm saying it to be outside. I get that off the phone. Were you at work? No, I was at home, but working from home.
He was on a call.
Interesting. No, I'm a radiologist. I put people to sleep, but
That's not what he gets paid for.
that would be interesting. That's a sideline.
It'd be fun to do that remotely. Arlene and I are going to Elvis in October.
Okay.
All right. Yeah, so I'm sure. All right.
No, is her name?
Okay. All right. We'll start off for what's up for the next time. I'm going to talk a little bit about June, July, and a little bit of August. So let's begin. Basically, for the planets, Mars and Venus is going to be strictly just an evening type of planet. Saturn won't rise until after 12, since we're pretty late in the month already, so Saturn will start to rise after 12 a.m. And Mercury is not going to be observable. Loud here. It's mostly going to be for the southern type of people, southern continent, to be able to see it. So again, Uranus will be in the morning sky as well as Neptune. Now for the month of June, we do have a few events. Of course, we have the full moon that just started on the 4th. We're pretty late in the day, so let's just jump right now. June 18th, we have the new moon. All right. Saturn, we're going to be in its retrograde motion very shortly, or already has. We have the summer solstice as on the 21st. Even though it says 22nd, Venus and Mars are going to be south of the moon, but if you take one day earlier, it looks a lot better. All right, I'll explain more about that later. Okay, this I showed you guys last time, this hourglass kind of twilight kind of thing. We're in the gray part of it because the month of June it never gets dark enough. But next month it will start up again where it gets some dark skies. So if I begin with this here, just bear in mind that at 6 degrees, Judy talked about Noctilucous clouds there. So that's when it's going to start. It has started already. This is the season to look into it. So this is a different twilights. Again, for us, we never get dark enough. And even at 2 o'clock in the morning, there's a lot of other factors. Restaurants are open.
later in the evening, so unfortunately that's going to be a factor as well. All right, noctilucent clouds, as I mentioned before. So this is the season to look into it. It does happen a little bit in the morning as well. So if you haven't seen it, or maybe look at the pictures, I did mention this time about spaceweather.com. If you want to know predictions of it, but unfortunately one of the satellites is down. So we're using another satellite to kind of predict it, and you're just releasing the data to the general public. So if you haven't seen it, I do have a picture of it, which I think is going to be my next slide, right there, right next to the comet, view-wise. So that was early in the morning, and I just love that morning because it was just perfect. The comet, it was bright enough, and it was the only time it was bright enough to actually look at it. All right, now, okay, so this is today, as of right now. You can see Mars and Venus, just in the early evening part of it. You can see the sun is supposed to set right now, so that's when those two planets are going to be visible. So, and that's going to dominate most of the month. As I mentioned, on the 22nd, the two planets are going to be south of the moon, but this time, if you look one day earlier, they kind of form a nice little triangular there, which I think it looks a lot nicer. So the day before that same time, just before or just after sunset, we're looking at these things. The reason why I picked this, because then, what do we do? Okay, well, it's never going to get dark enough. What can we really look at? Well, this is the order of the slides. Okay, so after sunset, we have these happening. Then we have the nocturnal clouds that's happening. And then also, too, we have the summer triangular that's happening as well. So we have the three stars. And I got this big thing right here. I'm just blocking my view. So I can't see it. Deneb, Vega, and Altair as the three stars here for the summer triangular. Hopefully this animation is going to start. So it starts at Deneb to Vega, from Vega to Altair, and from Altair to Deneb as forms the summer triangular. That's tonight, right after 12 o'clock, right? This is going to happen. Well, you can't really see, I can't really see here, but you guys can see here. We do, well, we don't.
There's no way to get rid of that.
Okay. Starlink is going to happen around just before 5 minutes before 1 a.m. So we have a lot going on. So if you haven't seen Starlink, this is a good time maybe to have a look at it. And of course, in the down low on the left-hand side, we have M31 or Andromeda Galaxy. All right. Okay, so what else can I review if it's not going to get dark tonight? Well, we do have an increase in solar activity. As you can see here, the data, what's really happening with the data over the predicted value over the actual values are almost double than what the predicted value right now. So that's definitely going to mean a definitely increase in solar activities. So the aurora is going to be up. So here's a picture from last year's Star Party, right? I'm trying to do a time lapse photography. I didn't have enough time with the other project I was working on, but so there's the aurora that's happening. All right. So what about the weather? Well, again, I don't think we really need to look at it. It's going to get a lot warmer again. It's going to dip down towards the weekend, and then it's going to dip back up. All right. So otherwise, the weather's going to get real hot. Now for cloud coverage, and well, we do have some clear skies, but during the midweek, we do have some clear skies. On the weekend, looks like now we got some clear skies. Before it was pretty cloudy, but now we do have some clear skies for next week. And next week's going to cool off a little bit, so hopefully it'll help out. All right. As I mentioned, for the month of July here, we have, well, Pleiades, and then we have Jupiter, and it was Uranus. So that's early in the morning. So that's another thing that's on July the 13th, around 4 a.m. So I'm just going to pick certain events that's going to happen in the next couple of months. Because we have the barbecue for next week, so we won't do any meetings. And then, of course, August, right? We do have another meteor shower, which I'm going to mention about this, the Aquarius meteor shower here. Unfortunately, we do have the full moon, so it's a no-show. So it's nearly the full moon, but it kind of overlaps another meteor shower, right? So it starts just August 19th, but it peaks have August the 16th as the new moon, but it's August the 13th that we do have another meteor shower called Perseid. So again, but we were around the new moon, so that's a good sign that we will do some kind of viewing for this meteor shower, and it will be still warm. So I'm going to look forward to that. I'll talk more about it a little bit later. I was going to do a little bit more about time-lapse photography that I haven't captured with the meteor shower, but I'll do that in the next event. So again, so we do have some, Perseid meteor shower on August the 13th, I believe, right? And okay, so that's it. That's all I have for what's up for the sky of July, August, and June. Sorry.
Right, next up is what's new, Michelle Boyce.
Testing. Okay, my work is. Good. Okay, so I'm doing what's new. So this is basically shows the clunkiness of our universe, and this is from an article from Science News, and there's a new link that was found between dark matter and the universe's clumpiness. The universe is not as clumpy as we thought. It's a bit less clumpy, like smooth. And axions are a dark matter candidate that can solve this problem. So there's some, according to these people, there's a strong inkling that axions might be the ideal dark matter candidate particle. Basically, they have quantum mechanical wave nature of the wavelength can be on the order of the size of galaxies, which smooths things out. What are axions? Okay, this is kind of a busy slide. Because I didn't want to spend too much time on this, but I've talked about particle physics before, standard model of particle physics, and we know that there are certain fundamental forces in nature: electromagnetic force, electroweak force, which is W plus minus Z naught bosons, and the strong force, which are gluons. Each of these are particles that mediate these forces. So static electricity, that the electrons or nuclei, whatever that atoms get together in terms of charge, is the photon that mediates that. And it's due to a symmetry that these particles exist. There's a certain symmetry that causes these interactions. So in particle physics or quantum electrodynamics, there are three symmetries: parity, charge, and time, and I'm looking at charge and parity. So we can see here in this little box on this side, here, parity is just a mirror image. So if you have an object that's spinning like this, and you look at a mirror, it's spinning in the opposite direction. So that's a mirror symmetry. And then charge conjugation is where you change the particle from one charge to another. So an electron can become a positron. In other words, it flips its charge, and a positron is an anti-electron. CP symmetry is a symmetry that changes the charge and the parity of the particles. So it's both operations. So here I'm showing that you're familiar with electrostatic charge, plus and minus. Like charges attract, repel, and unlike charges attract. In quantum chromodynamics, which is the force of the strong interaction between quarks, that's mediated by gluons. Gluons, instead of plus-minus charge, they come in three colors: red, green, and blue. So the CP symmetry is much more complicated, but it's the same principle. So you're changing your color charge, but the charges get together and form structures. So there's a problem there in terms of just basic calculations that shows that there's a violation of the CP symmetry. It should be variant. And in order to restore this violation, we introduce a particle which is called an axion. So, long story short, which is a rather large mouthful, is that axions are a result of strong CP symmetry violation, the strong CP symmetry violation column in quantum chromodynamics. Okay, so that in a nutshell is where axions come from. In terms of dark matter candidates, I kind of like that because it's a natural thing occurring from a standard model of particle physics that we have tested fairly well. And so this is something that we haven't found, but naturally falls out of this theory. So it's one of my many list of favorite candidates. So that slide there, I showed that web-like structure. And basically, this is the structure formation. So if you imagine just at the Big Bang, you have normal matter, which is sitting down here. It's a very small fraction. In fact, everything we see in the visible universe is about 5% of all the matter that's there. And we have this dark matter. They all form equally, but then the dark matter interacts gravitationally and forms these, this mouse is not working well. It starts to form these local areas, and that attracts normal matter to those areas. So you go from this uniform distribution to this clumpy type of thing. And then as the universe expands, you kind of get this matter is being attracted, but you get this bounce back, and you get sort of like a wave, like dropping a stone in water. And you get what's called acoustic oscillation, which leads to foamy space-time. So this just shows, this is the cosmic microwave background, and this just shows one ring of an oscillation, where you have a dark matter ring, and then this little dark matter kernel. And that tends to form this structure over time. You get these voids, and on the outskirts of the voids, you get galaxy formation due to the concentration of dark matter. I often like to think of it as when you do the dishes and you have dish soap foam. Well, where the bubbles meet, those little lines where they meet, that's where galaxies form, especially at the nodes. And then the little bumps in the middle, not in your soap, is where they also form. So you get this structure. And there are simulations. So that was a simulation just using a generic mixture of dark matter. And this is a simulation using axion dark matter. And axions can become stringy. They can form string-like structures. And so this shows a simulation where you get this smoother structure due to these axions condensing out as the universe expands. Okay. And you always see this diagram, and I think it's worth pointing out how huge that is. So if we look, here's our little humble solar system, and then it's within 30 light years, it's within these nearby stars. And then here's the Orion spiral arm here, where I learned from Jerry that if you point to Cygnus and point to Orion, you're right in the middle, so that's where we are, the Orion spur. And then the Milky Way galaxy, we're sitting here. Then here's our local group of galaxies, which includes Andromeda and the Virgo cluster, and all that is that little tiny point there. So this is like a foamy space-time structure. And so dark matter is a fairly large chunk of hidden matter that we don't see, but we see evidence of it in many ways. Okay. Moving on to some exoplanet stuff. This is a multi-planetary circumbinary system. So quite often we would think of an exoplanet system with a star and then planets orbiting it. But we can also have binary systems. I'll come back to this slide. So we can have a binary star system and we can have a planet going around it as long as it's not too close. Otherwise will get kicked out of the system. Or we can have the stars separated by some distance and then this planet going around that local star. But this is an unstable situation where a planet is in between the two stars. It doesn't last as long. So there have been 12 circumbinary systems discovered thus far before this new one. This was Kepler 47, and only one elements in the habitable zone. So a habitable zone is basically you have a star, it's giving out light, and at a certain distance you have liquid water, the potential of having liquid water. So our planet is basically in the Goldilocks zone, not too cold, not too hot, just right. So there's ways of predicting that from the brightness of the star to get some kind of sense. This planetary system that was discovered has two exoplanets, TOI 1338b and C. And the binary star system is right here shown in this diagram. They orbit in 14.6 days. And then this little disk, which looks gray there, it's supposed to be kind of a red. If planet B were inside this disk, the orbit would be unstable and would be kicked out of the system. Planet B has a period of 85 days, and it's about 7 times the size of the Earth. And then planet C, which is close to the habitable zones, but not quite in them, is 65 Earth's mass and 250 days orbital period. So now this is the second multi-planetary circumbinary system. A couple of years ago, I talked about the Tatooine planet, which was basically two suns and one planet. So these were coined Tatooine systems. What I found curious looking at exoplanets is all these short orbital periods compared to Earth. And this is just a distribution plot. And you can see here's Mercury, Venus, Earth, Mars, and so forth. And this is just this histogram. And you can see there's a lot of exoplanets with very short orbital periods. And I'm wondering what life would be like there. 14 days to go around a star. That's just crazy. A lot of these turn out to be hot Jupiters, but nonetheless, it's interesting. It's a bimodal distribution. It's not quite well understood as to why systems would have these preferences. And my last one, which is kind of a revisit of Enceladus, one of my favorite places in the solar system. In terms of searching for life, I think it's the most accessible place, although it takes a long time to get there. And they discovered phosphorus. So Enceladus is this unique thing. When they had the Cassini spacecraft, they didn't even have Enceladus on the radar, but they noticed from analysis of all this gas being injected, see there's an E-ring that's actually formed from all this debris coming from Enceladus, and they detected something, and so they diverted the satellite to Enceladus, and they found all these gases that they said could be evidence of life. Did I put that on the next slide? Yeah. Excuse me. But what wasn't present in that analysis was phosphorus. But I want to just step back and look at that for a second as to why you would think. Why? So Enceladus is water vapor plumes, and that vapor's due to tidal forces because it's close to Saturn. It's a large gravitational field, so the moon rotates and it gets stretched like this, and that causes heating, and that's what causes the subsurface ocean that's suspected to be there. So Cassini was diverted to here, and they discovered all these trace chemicals, and they said these are signs of life. So I'm going to go through this somewhat quickly because I don't really want to get into biochemistry. But basically we base this on how we understand life on our Earth. So life as we know it likes to make ATP from ADP to do work. So it converts ADP, adenine diphosphate. Notice the phosphate or phosphor that's critical to so we can have life that exists in many places, and here this is life in smoker vents. So maybe there's volcanic vents in the bottom of Enceladus, and there might be little critters there. Who knows? These are aerobic pathways, so these are all possible types of cellular respiratory pathways of different forms of life. These are aerobic and then anaerobic, and more specifically, here we have this type of microbe that's found 2.8 kilometers down in a gold mine somewhere in Africa. And so it's living in an extreme environment in a way, and Enceladus would be considered somewhat of an extreme environment. And we see all these environmental chemicals that are going on in order to have this pathway work. So if we look at the environment of Enceladus, here is the rocky core and some volcanic activity or heating going on. And we have what's called radiolysis, which is molecular decomposition through ionization radiation. So you can have naturally occurring potassium, which decays. In your bananas, you get 1 or 2 potassium positrons every hour or so. Or uranium dioxide, which is in the ore down here. And these basically break up water into H2O2. And if someone asks for H2O, the next person should say, I want some H2O2 too, because that's fatal. And here, through pyrite and this, you can produce these sulfide ions, which is then feeding this pathway, anaerobic pathway for production of ATP. And this is from actually a research paper, and it's actually, if someone's into chemistry and stoichiometry, it's actually quite complex and interesting. But this is the model of aerobic channels through photoionization, producing this, and anaerobic channels through this catalyzation through pyrite. And then the jets being sprayed out, radiation hitting the surface, and also doing catalyzation and leaching, and then graphs and timelines and so forth. And all this, basically what's happening is the environment is creating oxidants through radiolysis, and the environment is also consuming those oxidants. But then we have life that's competing with that. So life also consumes some of those in products. And so it's a balance between how much is being created and consumed and how much energy is left to support life. And this is called a Gibbs-free energy. This is an old diagram of the tiger stripes. This is an infrared image. It's one of the first images that came out. It's actually kind of cool to see in the magazine. And so what that means in conclusion for this particular paper, which is earlier from the new discovery, is that this equilibrium leaves enough energy for cellular respiration. Now they did detect any O2, but they suspect that it just had something to do with the measurements. So anaerobic channels preferred. O2 is a different channel, aerobic channel, and so this just shows the different hydrothermal production. And the predicted microbial biomass for aerobic is 10 to the 12 to 10 to the 19, which is equivalent to 0.3 to 300,000 humans in mass. And anaerobic, 10 to 18 to 10 to the 19, about 30,000 to 300,000 units in mass. That being said, a lot of the biomass, subsurface biomass and ocean biomass probably exceeds the mammalian biomass or surface biomass, so just to give you a sense of things. That being said, then, to sort of sum up, this new discovery of phosphorus, which is it's vital for all life on Earth as we know it, and it was found in the E-ring, all that debris. It's used for the essential preparation of DNA, energy-carrying molecules, cell membranes, bone, I should say teeth, not teeth, seed, microbiome, and plankton. So life as we know it is not possible without phosphates. And this is the first first ocean world beyond Earth with phosphorus, so we must go back. Skip on, who cares about us? Let's go get some of this. Okay, well, that's it. For me, that's a quote from Prometheus. Okay, thanks.
Any questions for Michelle? So this is a prediction from modeling.
It's, well, basically, we're taking all our understanding of organic and biochemistry and how processes work, and so we see all these trace elements coming out of Enceladus. And so, with all our knowledge of geology and biochemistry and chemistry and so forth, planetary science, we can say that there's definitely these elements there, there's definitely an environment which can support life. We can't prove that life is there. But finding phosphorus there is also a good indicator just as well. And so it's worth the effort going there. And that's also true for exoplanets. Now we have the James Webb Telescope. We can look at exoplanet atmospheres and say, it's habitable, it looks like there might be life there. It definitely has the products of life. So there are certain signatures. And phosphorus is a pretty strong signature.
So does Earth's atmosphere have phosphorus?
That's a good question.
Does it
Probably not. No,
should it?
well, no, because these are subsurface ocean worlds and the water's being squirted out into space. So I don't think it would have as much. Because you have to imagine, if you imagine that there's a crust over the Earth and there's a pressure and it was blowing this material out, because it's in the ocean. Like, we don't really have phosphorus gas. We might have.
phosphorus gas?
Well, I mean, we don't have phosphorus in the air, like a lot of it. We did, I don't think it'd be around. I'm not an expert on that.
Concentration, I don't know.
Yeah, but I would imagine the atmosphere is extremely low concentration. Here we're talking about spraying of water coming out of cracks, crystallizing into small ice crystals, and then forming the heat ring around. Yeah, and so now we do mass spectrometry analysis, and we find this investigations coming from the ocean. So this is more like maybe life created around ocean beds, and all that material in the medium, and then being sorted out. So it's like leftovers, but it's a trace of something.
Thanks very much, Michelle. So I believe that the next speaker still has to log in. Is that right? Yes. So, good time for a break. Well, we hope he logs in. It's interesting to see some people sitting in the audience are also logged in. Okay, so there's the people who are here. I guess we really can't have a conversation with most all of them next on the Zoom. No, that would be ridiculous. Okay. Eclipse of the sun on October the 14th.
In Albuquerque.
Pardon me?
It's in Albuquerque. It's the best place.
It's a partial here, but it would be a great opportunity for the members of RASC to show the sun in eclipse to members of the public. And we've ordered a slew of eclipse glasses that people can share at an outreach event. For sure, the museum is planning something, but they had a massive success at some point in the past. They had about 1,000 people show up to the plaza around the museum, and it was raining. So there is an interest in seeing even a partial solar eclipse, especially now the likelihood of sunspots is pretty high on this thing. So we have eclipse glasses coming, and I thought our eclipse expert here might say a little bit about what you can see and what
So it's a pretty decent show. I know there's a lot of us that are planning to go down and watch it where it's central and somewhere in New Mexico, cycling. But we still, Judy and I will make up a set of plans for the center that will frame what can be done. I'm thinking what we'll do, because it's on a weekend, we don't have to confront schools and all the other naysayers. We'll just sort of leave it. If you want to come to, say, Assiniboine Park and show your kids a partial solar eclipse, or if the university wants to do something, then we can work with the university. And we'll certainly work with the planetarium. So it may have 2 or even 3 venues where we might have eclipse classes available to people. And we really just need, like, going and showing people the sun during astronomy day. People bring out a telescope so they can look at it. And we have lots of telescopes that will do that. And for this one, you're not really so much interested in hydrogen alpha as you are in just white light view of this thing. It's going to be 3.5 hours long, lots of time for people to see it. Although most will want to close to central eclipse, which I think is around 1:30 in the afternoon, something like that. So everything kind of comes together to make a nice little show. And it's a bit of a, I guess, a practice for April's total eclipse, which will also be about a 50% partial view. So if you're not looking to go running off to New Mexico or Utah or somewhere else to see this thing, you'd like to sort of be a part of the center's efforts for this eclipse. National has pretty much thrown in the towel. They've given up on doing anything significant nationally, and they're basically saying every center's up to it itself. So we're even buying the eclipse glasses ourselves rather than rely on anything from national.
We are buying them from National.
We bought them from national, but they haven't got a grant to provide them. We have a couple of thousand.
Yes.
We ordered 1,000.
Yeah, thousands of orders. Yeah, they were 50 cents a piece.
Yeah, that's a good price there. It costs you probably closer to 90 cents each if you bought them direct from the manufacturer. So just think about it. When summer winds down, we'll start drawing up a set of more formal plans for the solar eclipse. And they're worth seeing. Even if they're only partial, they're kind of interesting. And it's a good way to get to know your neighbor, so to speak. Nice thing about eclipse glasses is you can share them around. You don't all have to have one of your own right there. So if we pass out, say, 500 at various venues, then we may even be able to collect one back again and reuse them.
They might be kind of wrinkled after 12 kids have pawed through them and put them on their ears. How many of you are thinking you might travel to see the annular? A couple, anyway. And others who aren't here. Anybody on chat going?
I bought this stuff.
Maybe not.
It's not my lot, it's,
Okay. So that's just something to keep in mind. And as Jay said, it'll be kind of a practice run for public outreach in April, which is actually a weekday event. So it's a little bit different, and whether the schools want to participate or not, that's a whole other issue. In the past, schools have been either hot or cold on whether they show anybody anything, because they're worried about safety and liability, but I guess we'll tackle that a little bit later. The other thing, since our guest still is not signed in, and he's cutting it close if he's going to, is that you may have seen a press release today, I think, or maybe last night, that Virgin Galactic is finally going to start commercial launches into space. And some of you might know that a long time ago I put a little bit of money on the table to get a ticket. So just if you're into counting down, I'm number 403 on the list. I don't think the research trips have a number assigned. 4 passengers go at launch. But at the beginning, they're going up once a month, they said. So I think I'm going to be about 90 before I go to space. But I'm going to go. Yeah, if I die first, he saves money. Does anybody have any interesting things they'd like to talk about? What have you been looking at recently? Who's seen Noctilucent Clouds?
Not recently.
Gail? This year? No, not this year yet. I know in Kaleida they saw Noctilucent Clouds. So maybe you need a super dark sky.
2 weeks ago, I was substitute teaching at a high-rate colony, and I brought my Vixen 114 atoll out in the mount and the solar filter on and showed all the kids sunspots, and then we had to talk about what are sunspots and yada yada yada. And the nice thing about the colony is that I don't have to worry about, it's just me and them, and that's it. And they're very happy to see me.
Right. Can people on the Zoom hear that at all? Just see. Show chat.
I bought a glass.
I'm not seeing anybody complaining
Solar filter.
about it not being.
Do you know how terrible those are? Haven't you noticed that?
Yeah, that's not a bad idea.
Yeah,
No, with the-
nobody's ever got anything less than a guardian in their pocket.
I do notice I've got one for my tenant.
So observing plans. Yes.
I just wanted to mention, radio was pretty well blanked out this morning, so it must have been a CME overnight or this morning. So we might see some activity tonight if it's dark enough.
There was something about the Aurora Oval tonight. It wasn't super big, but
Why did they say this?
not sure it would be. Which radio station were you?
Well, ham radio,
Oh,
pretty
Ham.
well from,
I grabbed your TV and it was blank too.
yeah, it won't affect that.
You have a rapid ear TV.
Didn't have a signal, there was no radio.
Way to go. Oh, there's our guest speaker. Hi, Eric. So we have to make him a co-host, is that right? That's great. So it's my pleasure to introduce Dr. Eric Rozalowski, who's a professor of physics and astronomy at the University of Alberta. His research uses radio, infrared, and optical telescopes to unravel the connections between successive generations of stars in nearby galaxies and the Milky Way. He enjoys teaching math, physics, astronomy, all of those at different levels, probably undergrad and graduate, and he lives in Edmonton with his family. Welcome to our meeting, Dr. Rozalowski. Yeah.
Okay, now is co-host. I'm concerned about the audio.
He's got the screen, which is great.
Behind you. You just need to hear it.
Here, we're not hearing you.
Yeah, just hang on a minute here, Dr. Rozalowski. It's not give instructions. Get it on to the system.
Can you try to...
Co-host.
aurora display that showed up last night and caused interference with ham radio stuff.
Oh,
If you get the plasma that comes up from the sun, if it's got the right polarity to it in its charge, it can sneak into our magnetic field and cause havoc. You just have to have these two things lighting up like slipping in and cheating. And it sneaks into our field. That's why you want to have the polar field of the sun flipped from ours.
We can hear him on Zoom.
what's that got to do with
Well, what happens is once that stuff slips in, it covers up the ionization in the atmosphere and ruins ham radio. Well, yeah.
Sometimes I put on my shortwave radio when I'm watching stars at night and get some faraway radio station. So it's kind of neat.
You notice that the WWD tax something, something important happens.
Especially in the shortwave, I used to get occasional Radio Moscow or English broadcasts, trash in the United States. It was great.
When I was working up north in the summer of
Mute is still on.
76, I found some Boston wire out in bushes right in the bush. Wire from the iron fire, and it just run it through the trees. And for the rest of the I was listening to
Hello? Is my side coming through okay? All right. I'm going to assume that things are working, and you're going to have to mute to keep me from getting real echoey. Well, thank you so much for that kind introduction, and for everybody for bearing with us through the inevitable joys of Zoom audio. It's a real pleasure to be here, be remotely here tonight to talk to you a little bit about the first images from the James Webb Space Telescope. And I've actually I'm coming to you as somebody who's had the privilege of collecting data on the JWST, and this is one of our images here in the background. And sort of over the next 35 to 45 minutes, I'd like to talk a little bit about what it is that makes JWST such an excellent space telescope and what the new opportunities for discovery are, and give you a little bit of an orientation as to how JWST is similar to and different from the telescopes that we sort of operate in our optical here. 1 second, I'm going to address a technical issue here in the room, and I'll be right back. Sorry about that. To get started, I think the exciting thing about JWST is that it is an infrared space telescope. And we typically operate in optical light, and the infrared means that is this corner of the electromagnetic spectrum that gives us a lot of opportunities for scientific discovery. Historically, infrared light came from a discovery by William Herschel, and it's a kind of experiment that you could do at home if you have a diffractive element. This little, probably apocryphal painting here shows the sunlight being refracted through a prism here and being dispersed onto a table, forming the characteristic rainbow. And Herschel's discovery came by taking these thermometers here and sliding them into the light and measuring the color of the light. It was a simple experiment. Does the light have different temperatures under these conditions? So he measured the blue light and figure out what the temperature on the thermometer color was, and then the yellow light, and then the red light. And the discovery of infrared light came from sliding in past the red part of the spectrum, where it looks like no light is falling, and he discovered there was a substantial amount of energy and radiation coming in there and provided heating. So he called this the infrared light. And as I said, you can do this at home. And if any of you are teachers or otherwise so inclined, with a prism and just a couple of thermometers, you can go and discover infrared light yourself. Historically, and something that I always find kind of fun, is after Herschel's discovery came out, a lot of people said, well, what's on the other end of the spectrum? And so Johann Ritter proposed that, well, on the other end of the spectrum must be cooling rays, seeing as the infrared was the heating radiation, past the blue light is the cooling radiation, which is just a good reminder that it's important to have a lot of ideas, even if they are not necessarily correct to get started. We've come to call that the ultraviolet corner of the spectrum, and that light actually carries more energy than infrared radiation. But not everything is right out of science at the first time. So this is a nice graphical representation of the entirety of the electromagnetic spectrum. Its light is characterized by its wavelength of radiation, and so this diagram is sort of illustrating the changing wavelength of radiation along here and giving it kind of the classic labels here. And so we can kind of check this out in some detail. Down here at the longer end, these are the radio waves in the spectrum. And as the wavelength of light gets progressively shorter, it moves to the microwaves, infrared, the visible light that we are able to see with, the ultraviolet, X-rays, and ultimately gamma waves or gamma rays. And so when we talk about an infrared space telescope, we're talking about a light that or a telescope that is characterized by the ability to detect infrared light right here. And this is just the way that we always kind of describe telescopes in astronomy. We have X-ray telescopes, or X-ray telescopes observe the X-ray, radio telescopes observe radio waves, and optical telescopes observe optical light. So we're a simple, we astronomers are simple people. But telescopes can look extremely different depending on the kind of light that they're trying to detect. X-ray telescopes actually require very special mirrors inside them because X-rays have a lot of kind of penetrating ability, and it's why we use them to see bones inside our bodies. And if you put a regular mirror, it will actually go straight through the mirror if you're trying to basically do a standard like Cassegrain telescope or something like that. Instead, what you need to do is you build your optics to do very gentle focusing of the radiation, kind of coaxing the light down to form a focus here in a detector. So the X-ray telescopes often use these nested parabolic reflectors and use small angle light to bounce. In contrast, radio telescopes look a lot like satellite dishes because satellite dishes are fundamentally radio telescopes. They are focusing elements that collect and focus radio light into receivers. So this is you probably can't see the radio telescopes here if you were looking at it on the screen, but this shows the very large array in New Mexico, one of my personal favorite telescopes. And what we see here is a wonderful thunderstorm, and the telescope is very happily observing straight through the rain, which is one of the best advantages of radio telescopes, is that it's 24 hours a day through most kinds of weather. Wind can be a real pain in the radio because fundamentally, a big radio telescope is a giant sail, and so it gets blown around in the wind quite a bit. Well, these are orientation to different types of telescope across the electromagnetic spectrum. But why do we need a space telescope? Well, coming back to the diagram I have here, the keen-eyed among you may have noticed that there's this extra trace along the top. And if you can see the teeny tiny words there, it says atmosphere opaque to wavelengths. And this is just illustrating that the Earth's atmosphere doesn't let light through at all wavelengths. We love this in the case of the ozone layer because it keeps the sun's ultraviolet radiation from disrupting our biologies, giving us skin cancer or worse. The X-ray flares from the sun get blocked in the atmosphere of the Earth. And in fact, the Earth's atmosphere only blocks certain, or it only transmits in two main wavebands. The first is the optical, which is arguably why the optical is visible radiation. It's what we can see, and it's what our star is putting out. So it's giving off lots of visible light. And if you want to use that visible light, and you're a species trying to develop sensorium to see the world around it, this is a good choice of wavebands to look at. And then the other place where we can see the space is the radio. And in any other part of the spectrum, we need to make sure that we put our telescope up above the atmosphere. And so this is the infrared section of the spectrum. And you'll notice that there is a few spikes here, and then a fairly opaque atmosphere at longer wavelengths. So we need a space telescope, and here's one. So this is the artist's rendition of a deployed James Webb Space Telescope. Like many people, you probably followed its deployment after its launch. It was a very tense period for those of us who were excited to use the Space Telescope, but it deployed successfully, had very, it exceeded performance and expectations through its launch and its engineering phases. And this is an artist's rendition because it is deployed out beyond the moon. And so getting something else out there to take a picture of it is kind of challenging. But why are we launching it all the way out there past the moon to deploy into this weird shape when we already have a space telescope here at home? This is the actual photo of a deployed Hubble Space Telescope. And what is it about JWST that is better and requires new technology compared to Hubble? Well, it has really two big differences. The first is it's bigger. And if it's bigger, that means it's able to see more light. Telescopes are fundamentally light buckets. And it has better resolution. In the visible, you're no doubt used to seeing, and the conditions of the atmosphere setting how blurry an image is. But in space, no atmosphere. And therefore, we are limited in our resolution of our images, or fundamentally our seeing of our images, by the aperture, by the optics of the telescope and the wave properties of light across the telescope sets the resolution of the telescope. So, a little bit of math here. There's no quiz. I just yanked this out of my third year class when I put the slide together. But it had this nice figure that I had built. So I just kind of want to illustrate that with JWST and HST, we're frequently getting about 1/10 of an arc-second resolution. And when we're studying distant objects, the resolution is really essential for gaming scientifically. We cannot distinguish between these objects, and this sort of broad background resolves them into individual stars and other objects if we look in more detail with the better resolution. So bigger telescope, more light, and better resolution. And so this really, compared to previous infrared observatories, the comparable previous mission was an 1/8 of a meter, 0.8 meter telescope. JWST is 6 meters. So this is almost a factor of 10 improvement in resolution. And it's a lot like putting on our infrared glasses. So my graduate student was kind enough to make this meme for us, which illustrates sort of the previous observations of one of the galaxies here, and just the capacity we have for sharpening things up with this high resolution. So, bigger still is Space Telescope. The second one is that it observes in the infrared. And the infrared portion of the spectrum is really scientifically interesting. And the next part of the talk, I'd like to motivate why the infrared is such a useful place to observe light scientifically. Well, first, I want you to understand, and you probably have this in your head already, but I'd like to just illustrate that most of the time when we're looking at these images, we're going to be viewing them in color. But we can't see the colors. These are infrared light. Our eyes, by definition, don't work out there, which is why William Herschel had this great innovation in discovering light beyond the visible. So I'll be showing you images that are color composites where we will take 3 separate black and white images that are fundamentally tracing the intensity of light, and then combining them together into a synthetic full-color image. And we almost always use the convention that the shortest wavelength of light is blue, the middle wavelength is green, and then the longest wavelength is red. So it kind of preserves the ordering of the spectrum, even if we are lying about exactly where, the colors that you would see. We'll often also present images that use a color table like this, where the intensity of the light and sort of how bright it is just representing a pretty version of what is fundamentally a black and white image. So with that as preface, let's talk a little bit about the infrared. It gives us 3 main advantages compared to observing in the optical. The first is that the infrared is able to pass through dust, more on that later. I can see cold objects, and it is a witness to the visible part of the universe after the cosmological redshift. So, step 1. Infrared allows us to see into new places, and it's really seeing through dust. And there is a lot of dust in space. This is one of my favorite regions to study. This is in the constellation Perseus. These are a beautiful, ultra-deep, wide-field image of this region. And if you look, you see this fantastic background of stars with a bunch of stuff that's in the way. And that stuff is the dust. It's the sort of, it basically looks like smoke with some kind of darker individual clouds. These are sometimes called dark nebulae, but it's fundamentally dust clouds. And this dust is the pollution of stars at the end of their life. So typically a star of our sun's mass or larger in its red giant and late-stage red giant phases will be throwing off carbon-rich winds, and these winds boil off the surface of the star, and the carbon and the hydrogen in them coalesce to form hydrocarbons, which are basically, the dust grains that we're talking about are soot. So it's black, kind of allotropic carbon, the kind of stuff that you would find on the inside of a wood-burning chimney or the inside of your charcoal grill, except typically a little bit smaller grain sizes. But that's kind of what is scattered throughout the universe. Stars are kind of dusty polluters at the end of their lives. They burn very clean during their lifetime, but at the end, they make a lot of dust. But because the size of dust grains is typically about the wavelength of infrared light, this dust grain is actually an interstellar dust grain that was captured in a sample return mission while it was flying through our solar system. So they caught it in some gel and landed the gel sample. And so this is something that was born in another solar system that just happened to be blowing through our solar system when it was caught. And this one is pretty big, but typically they're about a micron across. And since it's about the same wavelength of light, light that's longer wavelength than the dust grains passes through it. And this is illustrated here with one of these three-color composite images. In the left-hand image here, I've shown you the color composite that's using three colors of visible light. Blue, bluish, yellowish, and reddish light get composited together here. And there's this big dark dust cloud, kind of like what we saw in the Perseus image over a while back. But if I replace the red part of this three-color image with an infrared filter, suddenly you can see straight through this region to all of these stars in the background. And they're only visible in that infrared light because it passes through the dust, whereas the visible light gets stopped by it. So suddenly we can see the light we can suddenly see through into the depths of these regions. So this is a pretty iconic image. This is a visible image of a portion of the Eagle Nebula. This is called the Pillars of Creation. And I showed this to my class, who consists of teenagers and 20-somethings. And they said this was the most famous Hubble image that you've ever seen. And they were just kind of like, what are you talking about? Because this came fairly early in the Hubble mission. So I recognize this as one of the iconic Hubble images. And what is happening here is we see the effects of radiation from the star off in this kind of, off the picture to the sort of upper right direction. And the strong radiation from this massive star is kind of boiling off the dust and gas associated with a cloud of material in the interstellar medium. So it's kind of getting carved away. But the critical point for this is that we have the remnants of this cloud that's kind of being peeled away by radiation. And as we look, maybe sort of zoom in here, we can't see that much. There's all this dust sitting in this cloud. And that blocks the visible light, so we can't see through it behind it. But now we can go into the infrared and turn on our JWST imaging capabilities and look at the exact same region, and suddenly we can see straight through the cloud to everything in the background. And all of these stars here suddenly leap out so that to be infrared. So we can see into new places that otherwise dust will obscure. The next big advantage from the infrared is that it sees cool objects. And cool objects are brightest in the infrared. So planets, protostars, all of these things show up in the infrared. So to sort of fill out this concept, we like to think about this in terms of the temperatures of the emitting objects. And this is a picture of a forbidden light bulb. You can't buy these anymore. So the way we made light from Thomas Edison to about 10 years ago would be to take an electric current, run it up through a wire across this little tungsten filament right here, and then the current would go down. And that tungsten filament would resist the electrical current. It would get really hot, reaching temperatures of about 3,000 Kelvin, and it would emit a bunch of light. And that light would come out in the visible and the infrared. And it kind of has this sort of characteristic shape or color to it. And part of the reason why we no longer use these light bulbs or sell these light bulbs is that the tungsten filament produces visible light, but 90%, 97% of the energy coming from this light bulb would come out in the infrared, which you could discern by putting your hand onto a lit light bulb, realizing that was a mistake, and then removing it because it's putting out so much heat. So this is, the basic principle that we use in astrophysics as well is this thermal radiation. This plot is a plot of the solar spectrum. Our sun has a surface temperature of about 6,000 Kelvin. And so this is a plot. On the x-axis we have the wavelength of the light and its corresponding colors are sort of shown here in the rainbow. And then how much light we're getting is the vertical axis. And so the sun spectrum here is shown in this white line with some characteristic spectral features, and the curve underneath shows what we'd expect from a perfectly hot object with a temperature of 5,777 Kelvin. And the sun gives off lots of visible light. Most of the brightest part of the solar spectrum is in the visible, right here in the green, because as we all know, the sun is green. And then the long tail out here is the sun's infrared radiation. So this radiation out here is in the infrared. And the wonderful miracle of physics says that the hotter the object is, the more this curve kind of shifts into the blue, and then cooler objects are shifted into the red. And so this is several curves at different temperatures, and this sort of chunks the spectrum up into what we can see and what's in the infrared. And you'll notice this cool little object down here, a mere 3,500 Kelvin, kind of like our light bulb, and it's giving off most of its radiation out here in the infrared part of the spectrum. And so this shapes the color that we see to a point where we're kind of familiar with this if we're buying light bulbs today. They are typically sold with a color temperature, and it's not just 3,000 Kelvin like you would get from a tungsten filament light bulb, but instead you can buy a whole range. Usually you can get a 3,000 Kelvin light bulb and 6,000 Kelvin light bulbs. For 6,000, that's about the color temperature of the sun. But as we get cooler, the light gets redder and redder because of this effect. So while some objects are quite cool and dark in the visible, like this is Neptune here, and the light that we see from it is reflected solar radiation. It doesn't put out a lot of heat, or it doesn't put out a lot of visible light, but it's still a warm object. Cooler than the sun, even and the Earth, because it's out in the icy part of the solar system, but it is still substantially warmer than the background temperature of space. And so when we observe it in the infrared, it lights right up. So this is the JWST image of Neptune, and what you can see is we see all these warm little patches here, and those are the storms on Neptune where it is whipping up and bringing in the hot material from the underneath parts of the planet, the interior of the planet, and that corresponds to these dark regions here. Those are upwelling zones on the planet, and they light right up in the infrared. And in fact, we have the rings also show up quite well in the infrared, and that's more given the nature of the light that they reflect. This is the moon Titan. This is the composite image from the Cassini mission and the Huygens probe. And if we look at it in the infrared, we can compare Titan in two images. So this was the on-site image of the telescope, of the moon. This is on November 4th of last year, the JWST image, and then this would be the visible image here. And we can see that you can kind of compare and see the warm parts of the planet lighting right up in the infrared here. So the near infrared parts of the spectrum are what allow us to see through the dust in these regions. But the dust is also heated up. And so this is what we're seeing when we're looking through the dust, and we're seeing some reflections along here. If we go into farther, longer infrared wavelengths, the stars aren't giving off as much radiation there, but the dust is kind of giving off most of the light. And so when we do that, we get this nice, almost spectral view, which is tracing out where the warm parts of where the warm parts of this cloud are, as visible in the dust. Similarly, we can see this is the infrared radiation of the Tarantula Nebula in the Large Magellanic Cloud. This is the 30 Doradus star star cluster, and then you can see the dust heated up all around it, and then the star is visible through the gas clouds that were not visible there in optical wavelengths. This is one of our favorite targets. So I work in a team, and we had observed and collected this visible data with the Hubble Space Telescope. This is the Phantom Galaxy, or M74. I've never seen it through an actual optical telescope from the ground with my own eyeballs, but I understand it's one of the more challenging Messier objects. But this is M74 in visible light with massive space telescope in optical, and you can see these really prominent dust lanes in it, tracing out the spiral structure here. And when we observed this with JWST, we were quite struck by the fact that those dust lanes just light right up. And so we shift from being able to see the stars to seeing the dust. So this is one of the great features of JWST, is really picking out all of this dust in its thermal radiation. So the final advantage of JWST is it allows us to see the visible part of the spectrum where stars give off most of their light, but we can see it after cosmological redshift moves that light from the visible part of the spectrum into the infrared. And this is essential if we're seeing regular galaxies at the most distant parts of the universe, because the universe's expansion has stretched out the light while that light is coming towards us. So to give you a sense of what I mean by cosmological expansion, I want to do a PowerPoint science experiment. Behold the universe, or a rough approximation thereto. The stars that you see here are supposed to represent galaxies, but the program only has stars in it. It doesn't have cute little galaxies. And what this is supposed to show is the state of the universe at some time. And then, a little bit later, the universe is expanding. So I'm going to take the same universe and plot on top of it the universe after it expands by about 10%. And when I do that, I see this. The yellow is after the expansion of this 10%. And I'm going to anchor right here on this little center galaxy. And what I notice is it looks like everything in the universe is retreating away from me here. And in fact, the farther away I am, the more that the galaxy appears to have moved away from me. True up here, and it looks like we're the center of the universe. But I can take the same field of galaxies, expanded by 10%, and anchor it down here on this little star instead. And when I do that, the universe looks like this. Here, the stuff that's close by has shifted away a little bit, and the stuff that's farthest away has shifted away much more. Same thing goes if I'm up here. Looks like we're the center of the universe, and everything is shifting away from us. And farther, more distant systems are shifted further. And this is happening over time, so it appears like those more distant systems are moving away faster than the nearest part. And in the business, we call this the Hubble flow, referring to the flow of galaxies away from us. But that's really just a manifestation of the expansion of the universe. So every galaxy seems to be at the center, and more distant systems appear to be moving away from us faster. And that moving away from us and the stretching of the radiation means the light from those galaxies has been shifted. So, shifted redward. And that's what this little image is supposed to show. To orient you, this underlying grid is supposed to represent the space-time of the universe. This is a distant galaxy. This is Earth. And we're going to kind of undergo cosmological expansion. And this is kind of hard to look at. It looks like we're getting closer and closer. But what this image shows is that the Earth and the galaxy, I'll play it a second time, are staying the same size, but as space is expanding underneath it, the radiation is getting stretched out and shifted to the red. It kind of looks like we're zooming in, but the objects are remaining the same size, and the underlying space-time is pulling those things apart and shifting the radiation into the red. Well, if we have a galaxy that's emitting a lot of visible light from stars like our sun and bluer stars that are hotter and more massive, if it's really far away and has undergone lots of cosmological expansion, as the light is traveling from that galaxy to us, it's going to be shifted, and it's going to be shifted into the infrared. So that was one of the earliest sets of results coming out of JWST, and it continues to be this amazing set of results, is finding the earliest galaxies. This is an example of one of the fields that's studied. This is a galaxy cluster and imaged here, and they saw this beautiful field of galaxies. There's 2 detectors in this camera, so this is just 2 different parts of the sky, this giant crowd of a massive galaxy cluster. And the thing that people were excited about weren't the galaxies in here, these tiny little red smudges that are called out in these boxes here. Here's 1, here's 2. It's just these little red dots because they were really red. They looked just like galaxies. Let's zoom in on one side. Just these little red smudges. But they are basically look like galaxy light that has been shifted a lot. And in the business, we'll often give it the letter Z, indicating the degree of shifting. And so this means that the light here has been expanded by basically 1,050%, 10.5, a factor of 10.5, technically plus 1, so a factor of 11.5 longer light compared to what has been observed. And so that takes 500 nanometer light and scales it out by, like visible light, and scales it out by a factor of 10 to like 5 microns, and right in the JWST Pascal. So this is starlight after it moves across the universe. There's been a lot of follow-up here. And this is another galaxy where they have really confirmed that these are indeed galaxies seen in the absolute earliest parts of the universe. And so we really sort of confirmed them. And there's lots of them. And kind of interestingly, lots of them. So let me give you a little bit of a story about how these galaxies form. And this is a movie. Not yet. But this is a computer simulation of how the universe is expanding. And so as we're how the universe is forming galaxies. I'm going to pause it for a second and sort of tell you a couple things. First off, let me stress, this is a physics simulation. The second thing is that the universe is expanding, but the creators of this video did not want to include that expansion so that we could keep track of things. So we're kind of zooming out as the universe expands so that it looks like it's fixed. The universe is also not rotating. We're kind of flying through the simulation of the universe. So it's just an artistic interpretation here. The thing you'll want to keep track of is time since the Big Bang. That's down here. It says 1.1 billion years. And this is showing the action of gravity as a smooth universe at the very early universe starts to fall down under its own gravity. And it collects into these long filamentary structures. With their intersections, you see the formation of galaxy clusters. So those are sort of seen here. And so material flows into these clusters and builds up galaxies. And then those galaxies have stars and black holes in them that start to heat the universe around them. And And that's the view that you see now. You see these explosions and these kind of flickering light as bursts of star formation heat up everything around them and kind of give feedback, and indeed heat up the universe as a whole over its lifetime. And so the point here is we have good physical understanding, so much so that we will spend millions of CPU hours, a huge chunk of compute time, exercising those physics equations from a very simple initial state and just running forward through the model to build up our models of what the galaxies are in the universe. And so over the course of time, as we get closer and closer to the present, we start to see a universe that looks more and more like our own. Here focusing on the gas, but as we get on a little later, we see more galaxies. We sort of focus on the formation of structure in the universe. But when we're observing with the James Webb Space Telescope, we're not observing these nice clusters of galaxies that you see here, but instead we go back in time to a mere 1.5 billion years, that's close enough, after the Big Bang. And we see all these galaxies. And we can take our numerical simulation and we can count the galaxies. We know everything that's happened in this numerical simulation. We can count them. And this is the best model of the universe that we can afford to create. And it has agreed with every observation that we've made so far. But when JWST turned on and started counting these galaxies, we found a lot of galaxies. We found a little too much. Not something that's going to break physics. It tells us we're on the right track. But we're finding out that we have just a few too many galaxies in the actual universe compared to our computer universe. And I love it. This is where science actually happens. Science is boring if you always get the answer that you expect. This is telling us that we weren't quite right, and we have to revise our understanding in some way. So one of the things that JWST's done is it's really kicked out a bunch of new results and spurred discovery, because we know what the universe looks like now. And so we can change our understanding and sort of critically evaluate where things are going wrong to figure out how things are, need to be corrected to improve our scientific understanding. So I'd like to ask, how am I doing for time? I have one more chunk I can talk through, but this is a wonderful stopping point if you'd like to do some questions.
Go ahead.
Yeah.
Sorry, I just had to unmute there. I got feedback from the room. They say go ahead.
Thank you, Gabriel.
Yeah, thank you.
All right. The next thing I want to talk about, so this was one of the big things that we got out of JWST very early on, was the discovery that there are lots of early galaxies. The other big thing that is coming along far more slowly, but I think is going to be bigger impact over the course of JWST's life, is the study of exoplanet atmospheres. And I really think that this is something to be watching as we go through. So JWST is often observing other planets in other solar systems. It's one of the main things that we're observing. And the first results that were kind of exciting from JWST were studying exoplanet atmospheres by using this idea of studying stars and their planets as their planets undergo a transit, passing in front of the distant star in kind of a little mini eclipse, and then moving out. And we can observe the light before the eclipse, during it, and after, and monitor the light from the star very carefully. And what we see here is a little graph like this. And so what this is showing is the brightness of the star at sort of 100% is outside of the planet. And then when the planet moves into transit, you can see the limb of the planet moves in, it blocks part of the star, and then it moves out. And it kind of has this sort of dip here because of the limb brightening of the star. So it's not a flat bottom, but a little bit of a curve. And what we do is we can just sort of monitor the shapes of this light. But what's kind of cool about it is we can actually observe it at different colors of infrared light. In the red light, in the blue light, and kind of in the middle of the green light. And so what's happening is you see that the red points here have less of a block than the green and the blue points. So this is telling us that the planet's atmosphere is kind of letting through some of the light at that wavelength that is otherwise being blocked by the other wavelengths. And so this gives us this unique opportunity to do the spectroscopy of other planets' atmospheres and measure the different chemical compositions of it. Because in spectra, there are kind of the unique fingerprints of atoms, but also of molecules. And this is where the infrared gets really exciting, is that a lot of molecules have strong absorption features in the infrared. So what's showing up here is another spectrum of light. So we measure the blockage during a transit of lots of different wavelengths of light. And we can see all these different molecules here. Some kind of boring ones like water and carbon monoxide. These things show up in all kinds of parts of the planetary atmospheric spectrum. And in fact, it's these absorption features that keep us from seeing through the atmosphere in the infrared. We have a lot of water in the atmosphere that blocks infrared light. And so we end up with more blockage at the water lines than in between them. So this is the amount of light blocked. It's kind of flipped upside down from the previous graph, represents the previous graph. But this shows us where the water is. And so we can measure how much water there is in this spectrum, how much carbon monoxide there is. And what's neat is you think about, well, what else is in a planetary atmosphere in the infrared? So this is showing the infrared part of the spectrum of our planet. And it shows the amount of light that's blocked, and we can see these different features. So we were looking at the carbon dioxide features and some of the water features through here. Here's some more CO2. And so one of the features that's really exciting that shows up right here is this ozone feature. And ozone is an interesting molecule because Earth has a lot of ozone in it. And it has a lot of ozone in it because it has a lot of O2 in it. And those of you who may throw your memory back to chemistry knows that oxygen is, well, it's the definition of an oxidizer. And so if we actually have something like around that's combustible, that oxygen is going to combine with it, it's going to burn up, and it's going to go into mostly CO2 and water. So the default chemical state for material, absent some other effects, is the fact that we can actually see we will combust into mostly carbon dioxide and water. But the Earth is unique. The Earth has photosynthetic life on it. And so the plants have reprocessed our atmosphere to the detriment of a lot of the species that were alive at the time. They've reprocessed the atmosphere to be oxygen-rich, and it is a byproduct of our atmosphere being oxygen-rich that produces a strong ozone feature. And so, unique among the inner planets, Earth has this ozone feature, and it is a biomarker. It's not, you can contrive a few cases where ozone is indicative of some just weird chemistry, but if we measure a strong ozone feature, it's an interesting indication that there could be life this planet here, Earth, or on another one. And with JW's team, we have the capacity to make these measurements and actually sort of unwind it. So we're going to be measuring the atmospheres of other planets and other solar systems. We're going to find the diversity of different types of atmospheres. And we may, in fact, over the next few years, come across something that looks a lot like a set of biomarkers and possibly indicating extraterrestrial life, which I think is really wild because this is like the kind of thing that you might expect. If you run the numbers, you might actually think that there's a lot of maybe life out there. Maybe not intelligent, but there could be a lot of green goo. And if there's a lot of green goo, it may be showing up in the ozone. So this is something that I'm keeping my eye on as we're going forward. I think it's really kind of an exciting new direction that we could end up seeing JWST things. All right, that's what I wanted to say here. Thank you so much for listening. And if anybody has
Thanks so much for giving us that talk. Are there any questions from the audience or from the Zoom audience on the chat? So I have a question. I can always have a question, right? I wondered about the three false color wavelengths that you're using. Is it infrared, A, B, and C?
bands, like the old ABC infrared designation bands. I mean, they're all infrared light that we're using them, but it depends, and I definitely swept that under the rug. If we look at this image here, this is a composite of 7.7 micron light, 10 micron light, and 21 micron light is showing up as the blue, green, and red parts of this image, respectively. JWST actually has many different color bands on it, like 20 different ones, and so we're a bit of picking and choosing. Images like this one, which I didn't show you, is compositing light at 2 microns, 3 and a bit, and then 4.4 microns. So we are, the correspondence of the colors that I'm showing you relative to these specific bands is changing through here.
That would be good to know, I guess, when we're trying to think about what the images are showing us, because the standard wavelength pattern is changing all of the time in those images. I do microscopy, so in that field you tune for many different wavelengths for a different reason, but each of those contributes more knowledge, and sometimes it's your brain that needs help compiling all of those things together, so the computing power must be massive.
Yeah, it is quite substantial when we have to build up. And I'm actually trying to pull up something that's not in my talk, but I kind of went, here we are. I'm going to pull up another image real quick. I just want to, so when you're seeing a lot of these public release images, stop this share. And I will share the screen down here. This is one of the images from the JWST sort of press release and everything. And what you can see is often they'll park down here at the bottom a little designator. And this is how I'm getting the answers that I'm giving you, is it tells you the colors here, and they're using the JWST inside band codes to indicate them. But the secret is you just divide by 100. So this is 7.7 micron, 10 micron, 12.8 micron, and 18 micron. And then they plot them in the colors that they're showing them in the image. So if you want to find out exactly what wavelengths of light there are, the public release images often come with this little band designator in one of the images. So you can actually see it and then interpret it without having to kind of wonder. It's secretly baked in.
Any other questions? Yeah, we have some from the audience.
telescope has been limited by the strength or functioning of its gyroscopes. Now, is the JWST limited by the gyroscopes functioning well, or by the amount of helium left in it? What's going to go first?
The lifetime of the JWST mission is fundamentally limited by the amount of propellant it has on board. It does have gyroscopes, but and they may end up going. There's lots of things that can fail on a space telescope, but for now, JWST is limited by the fact that it is actively maintained in its orbit with some propellant. So it's a spacecraft, and it can rocket around. And eventually, it's going to lose. It's in this little equilibrium point in dynamics called the Lagrange 2 point, and it doesn't necessarily stay there. It will eventually get kind of pulled off unless it has propellant to kind of keep it in this equilibrium spot. It'll get pulled out of it by basically planetary tides. And then that it will sort of drift off. It will probably be useful for a little bit, and eventually it will kind of fly away. So the station keeping and propellant is limited. The greatest news that the astronomy community received is that we didn't, this was not only carried, the minimum spec for JWST was that it should operate for 5 years and have enough propellant when it arrived on the station at 5 years. And it had to slow itself down when it got to where it needed to park its part of orbit. And it got there, and the launch went so well that it landed and had enough propellant to stay on station for 20 years. So we're going to get, hopefully, 4 times as much JWST as we originally expected. And I think that that's the best news that the community's received in a while.
Do you have a question, Mark?
Okay. I have a question about the color assignment by bandwidth. Now, is it a logical assignment like the prism assignment, like visual light, or do you actually, you could assign any color to any bandwidth you choose, but it seems like there is a pattern. And is there a name for the pattern or some structure to that?
Assign bands to colors in wavelength sequence.
Okay.
So, while they're not blue and red, some light is shorter in wavelength than others. And so the short wavelength light is what gets the bluest colors, and then the longest wavelength light gets the reddest colors. And because of the thermal light, hotter objects being bluer, typically what that means is that the stars that we see in an image that are bluer in the infrared have more short wavelength radiation. And then the ones that are a little redder have less short wavelength radiation and are cooler. And so that actually works here. So this blue star up here is hotter than this sort of more reddish yellow star here. So we usually use that, and that allows us to kind of interpret the colors. That being said, it doesn't always line up just like that, but the convention is usually to assign them kind of in wavelength order, even if that's not the exact colors.
Okay, thanks.
Other questions? So I'll ask another. How is the JWST groups, there must be many groups, but how are they deciding what to image? Because it seems like there's an awful lot of sky out there, and they could really image just about everything.
We spent a lot of time doing this. The JWST is like all telescopes that we use kind of in a professional capacity that have limited resources. We assign those resources competitively. And the way you put it together is you have to write a proposal. And I'm going to share So this is a proposal that I submitted and was approved in the most recent cycle of JWST time allocation. And the way it works is all the astronomers who want to use the telescope put together something like this. And so we use the computer program to design what can JWST do, and then we basically just write words to say, we think that JWST should, in my case, look at M33, the best galaxy ever, and it should make some observations in the following bands. Near imaging, near can imaging, here's those band designators I was talking about, and it should do it for 10,000 seconds. And then I write a very boring 8-page document that goes through and explains all the reasons why we should do this with JWST. And they take 1,700 of these proposals, and they put them all together and farm them out to committees, and the committees take them and they rank them and they say, this proposal better than this proposal. This is basic, and it's judged on which ones will give us the most benefit for science. And then we pick the ones that are, the most beneficial, with some errors, and, we'll say. And you try to curate a portfolio of science. It's going to be pretty exciting. And then the top 10% or so get accepted and put onto the telescope, which is very exciting when it happens. And, as you can see from the amount of text that you have to write, very disappointing when 9 times out of 10 you end up getting it rejected. So that's how we do what we do.
I've been there myself, both things. Objection and not so much. So there's a question from the Zoom audience. Have the data from the JWST modified the Big Bang Theory? And if so, how? In 5 easy paragraphs.
So it's, they have not strongly modified the underlying assumptions of the Big Bang Theory. There is some concern with the details. And the details that we're running into, JWST is kind of related to, but not directly addressing. In that we kind of have 2 separate ways of judging how the universe is evolving, 2 different kind of lines of reasoning. They don't quite agree. And JWST could be kind of in the middle for helping to resolve these issues. It hasn't done so yet, basically pickling between these 2 things. And we're talking about it's 5% disagreement, but it's still a problem. You need, science is always looking for what's the flaw, what's the problem. And that 5% is a problem. And so what JWST is doing is, the problems it's raising is more about how do early galaxies form after kind of the Big Bang Theory comes together. It kind of asks what our understanding of actually how the gas in galaxies gets turned into stars and heats things up, and how the black holes at the centers of galaxies form. That's what it's really kind of calling into question and asking us to revise here. The Big Bang Theory itself, JWST, I think, is going to give us more answers to whether this one line of reasoning is correct versus this other.
I seem to recall it was 2 or 3 months after the James Webb went into its Lagrange 2 orbit that there was a report in the media that one of the mirror segments got hit by a meteorite. Is that true? And if so, how have the astronomers worked around that? How much of an impact has that on astronomy?
Well, the keen observer will note that there is no dome on this telescope. And there's no can that kind of restrict, Hubble was great because if a meteorite comes in from this side, it, bonks into the side, and that's good. Here, you're putting your mirror out there, and you're letting it get rained on by all the dust and junk in the solar system. So that's a problem. What shocked people people with that one was it was big. Like, yeah, there's tons of micrometeorites. Some are dust, all the way up to things that are proper rocks flying through space. And there are way more tiny little things and a few big things. And they got hit by a medium-sized thing and realized and thought, oh, this might be an issue. So what they do, and this is new from the first cycle of observations to the second cycle of observations, is they restrict observations with the telescope so that the meteorites are mostly blowing in from the back side. And they basically, you just turn away from the wind of rocks. And so it's, you can't observe in certain configurations. Like if the telescope, you could turn around and sort of stare off in this direction, but if it's blowing into the micrometeorites, you're risking your mirror more. And just since you want to preserve the telescope as long as possible, you sort of steer it in the other way. And it doesn't rule out any part of the sky, it just restricts the times of year that you can get to it, because as the telescope is orbiting around the sun, or the moon and the Earth are orbiting around the sun, it kind of changes the direction that the meteorite wind is blowing, and therefore you can kind of observe, you can come back in 3 months and you can still observe whatever you want to.
Other questions, people? Well, I'm not seeing any. I've learned a lot. I think it was a fascinating talk, and I really want to thank you for agreeing to give a talk on Friday night. And I hope you have clear skies, and I actually hope that you would end up looking at M31 through an optical telescope. Go to one of the RASC meetings and take a peek. It's fun. Okay, thank you very much.
All right. Thank you so much. Bye-bye.
Okay, that ends the formal segment of our meeting tonight. I think that we're still scheduled to go to Boston Pizza, is that right? Brian's arranged that, so if you don't know, some of the people go afterwards to have a beverage or a piece of pizza and chat stars and other things of life at Boston Pizza on Pembina Highway, just down to the south of